that. So now let us look at instead of 1D element like the slender bar or a plate, if I consider a solid, for example, let me consider a cone. I'm going to consider a cone. So this is, let me consider the cone X, Y, Z axis. And this axis, x-axis happens to be axis of the cone. Let me construct the cone. This is the cone. Now, what is the rotation inertia of this cone about x-axis, y-axis, and z-axis? So I have to find out Ix, Iy, Iz. If this cone is to rotate about its own axis, what is the inertia? Rather, if it is to rotate about y-axis, means the apex is at origin, and this is going around the x-axis, y-axis, what would be the inertia? And if it is to rotate about z-axis, that means the axis is rotating in xy plane, what is Iz? So this is how do you find out? So for that, again, similar approach of considering an elemental rigid body and its quantity of interest and integrate it. That's an approach. So what is that I should do? I should consider here an elemental mass. So I will consider an elemental mass by considering a circular disk. And the circular disk is considered now at a distance from YZ plane, distance x, with a thickness dx, right? And this is my elemental mass. So what is dm here? How do I get dm? So dm will be this area into this thickness into rho, right? So rho into. So let us consider the dimension of this cone. The base of the cone is a, whereas the radius here is r. So this disk radius is smaller than this. R is 0 when x is 0. R is a when x is the height of this cone. So the height of this cone is from this point, what is the axis length till the x-axis? What is height? So h is height. The cone, right? Height of the cone. So now, how do I get my Ix? Ix to get, let me first get Iy and Iz, right? Iy and Iz. Or I would write like this. Ix is what is my interest would be integral elemental Ix. What do you mean by dix is elemental Ix? That means if this small disk is rotating about x-axis, if I know, then I can integrate that from x0 to h. x0 to h, and I would get my value. So what is dix? So dix is now this. So look at now, let me take this elemental disk out. And this is my x-axis. And this is my z-axis. And this is my y-axis. So if this is a disk, just now in the previous slide that we have looked at, if this is a disk, and about Iy equal to Iz is what is mr squared by 12 is what we have just now, mr squared by 2. Right? mr squared by 2 is what we have got it. Mr squared by 4. I'm sorry, mr squared by 4 is what we have got it if it is of circular disk that we have seen. For circular disk, if you just look at what we did in the previous slide, for a circular disk about xg and yg axis, it is mr squared by 4 and mr squared by 4. When I add, I'll get mr squared by 2 is about an axis perpendicular to the disk, circular disk. So now the orientation of this elemental mass with respect to x-axis, if you look at, x-axis is the perpendicular axis to the circular disk. So Ix would be mr squared by 2 for the circular disk when you write. Here this is not m, this is dm and this is di. Correct? So elemental, to say I put it like this. So dm into r squared by 2. So what is this integral? It is 0 to h integration goes over dm into r squared by 2. So r squared by 2 into dm. Right. So also here you have to see this variation of r is linearly varying. Slant length is a straight line. So the linear variation. So what is the relationship that I get? Here r is radius by x. R by x is what is equal to a by h. Therefore, r will be a by h into x. This is a linear relationship. So if x is 0, r is 0. If x is h, r is a. So that you get it from this. So I have to replace this in this integral. 0 to h, r squared by 2. So 1 by 2, let me take it out. And it is a squared by h squared into x squared and dm. So dm would be, what is dm here? It is this area pi r squared into dx into rho. So pi r square into dx is volume into rho is what is dm. And now here again this r, if I substitute, pi a squared by h squared into x squared dx into rho. That rho also, let me take it here. So it is pi a squared by h squared into rho into x squared dx is what is dm. So substitute that over here. This into dm. So if I substitute that, and these all are constant, if I take out pi a squared, already here there is an a square, so a square. So let me substitute and take out. I have to do it carefully. It's 1 by 2 integral a squared by x squared x squared into dm is pi a squared by h squared into rho into x squared dx. So now again in this 1 by 2, I have a squared that's become, this pi is taken out. Pi is taken out. So pi by 2, a power 4 by h power 4 rho is taken out. So it's x power 4 integral x power 4 dx. This varies from 0 to h. So this is your integration. Right. So now continuing with this integration, I would get rho into pi a squared a power 4 by 2h power 4 into this is going to be x power 5 by 5, 0 to h. So if I substitute, it is rho pi a power 4 by 2h power 4 into h power 5 by 5 minus 0. Now h power 4, there in numerator h power 5, so that goes off and I get rho pi a power 4 into h by 2 into 5, 10. So this is what is equal to I x of a cone. If cone is rotating about its axis, then the mass moment of inertia is given by this. So I have to, it is always better to write mass times the quantity. So what would be mass density into volume? What is volume of the cone? It is it is 1/3. So let me multiply here 3 by 3. So I will have 1/3 pi a squared h into a squared I'm taking out and this 3 I'm having it here. So 1, 3 I'm taking it here, and 10 I have it as it is. So now this quantity is going to be mass. So 3 by 10 ma square is what is Ix. 3 by 10 ma squared is what is Ix. So what is the radius of gyration if my cone entire mass is taken, shrunk and kept at a distance k, then it would be mk squared equals m into 3a squared by 10. So mass goes, so k would be under root of 3a squared by 10. So this is the radius of gyration. What is the meaning? If an entire cone mass is kept as a concentrated mass m at a distance k, and it's rotating about this, and this distance k is given by this. So I have got this Ix. Now how do I get Iy and Iz? We have to go with a similar approach, and I would leave it to you to derive as a homework. So what you have to do is look at the same problem, the same. So now I have to do Iy and Iz the same. So if I get Iy, I'll get Iz as well. Same expression. So how do I get for Iy? Same way here, like Dix I put, Diy I'll put. So that would be mr squared by 4. I have to take that expression and I have to do. So there, the important thing is the axis here, y-axis is an axis parallel to this y-axis. So I have to use my parallel axis theorem. So let me do that Iy, and you can work out for Iz and see that you get the same expression. Right? So now Iy would be integral diy 0 to h. So what is the quantity of interest that I consider for an element I know, and integrate that from 0 to h. That's the approach or general procedure of such integrations. So this would be what integral 0 to h, and here I have its own axis plus the parallel axis theorem I have to apply. So what is that? Is diy dash plus x squared into dm, where x squared is the distance. So x is the distance between the two axes. So you look at here about y-axis and this. So about this axis. So I have here an axis and this. So this distance is what is x. So x squared into dm plus about its own. This is my y dash axis now. This is my z dash axis. So about y dash axis. So that is what we have learned at the beginning of the lecture, parallel axis theorem, that I am going to apply here. So if I have to do that, I know that 0 to h, diy dash is dm r squared by 4 plus x squared into dm. So let me take 0 to h and dm out. So it's r squared by 4 plus x squared into dm. And in this, I know r is x by h. So substitute that here, integral a squared x squared by h squared 4h squared. If I substitute here, it is plus x squared into dm. So dm already what we had here is there. Dm is this pi a squared by h squared rho into x squared dx. That is dm. Pi a squared by h squared into what is that we have? Let me just look at here. Pi a squared h squared rho into x squared. Rho into x squared dx. So this is what I have to carry out this integration. So in this, what all constant that I can take out? So it's rho pi a squared by h squared. If I take out, I will have remaining here a squared by 4h squared, and this x squared goes in here. So that's become x power 4 plus x power 4 into dx. So that's going to be rho pi a squared by h squared. And here I have to take this x power 4 out, right? That also you can take it out. So it's going to be a squared by 4h squared plus 1 integral 0 to h x power 4 dx. X power 4 dx. So that's going to be rho pi a square by h square into a squared by 4h square plus 1 into this is going to be h power 4 5 by 5. So now this, if I modify and write in terms of mass times the quantity, what is that I would get is this. I'm going to write like this. Let me take this. I do not want h square term down, right? So I'm going to rewrite this in a convenient form. First, let me write for a mass. So what is the mass? Rho times pi by 3. 1 by 3 pi r squared h. Pi into r squared, that is a squared into h. Right? So this is mass. So this term I have to take rho pi by 3. So let me multiply by 3 divided by 3. So I would have now 3 out here. Rho is taken, pi is taken, a square is taken, and this is h squared, and this is h cube now. So h cube I can write it as h squared and h. So in that I take h here. So what is left is now 3 by 5. 3 by 5. So this 3 in numerator, whatever is there, by 5 is into I have here this I split it as h squared into h. H is taken h squared. So h squared, if I bring in inside, that's going to be a squared by 4 plus h squared. Right? So it is like that. So now this is going to be 3 by 5 m into a squared by 4 plus h squared is what is Iy. So the same is what I would get Iz as well, that you can